Shoot, that was the countdown for us actually starting. So pull out your notes if you would, please. I'm going to start. I just want to go through the reasoning behind all of this first, and then we'll go through the 205 stuff real quick. So, friends, come on up. Join us to do some physics up here, please. So, ever since trimester 2 started, we've been on this kind of singularly minded approach to physics, okay? And I don't know if you realized it because, I only see you for a few minutes a day, but the whole game, the whole time that we've been together, I'm just going to way back our brains up to the whole idea that the force of B on A, you can't see this, I know. I'll get it up there in just a second, sorry. Force of B on A is equal to the magnitude of the force of A on B. Right? We've been saying that for ages. I tried to convince you of it. We talked about it a bunch. We actually proved it mathematically. Do you remember with the two kids that were sitting on carts, and we did the math for that. So I'm hoping at this point that you're convinced of that. I have not been writing in this negative sign though. And I apologize for that. Negative signs sometimes scare people, and I didn't want to scare you. Then I realized after a while that I'm kind of like I've been a little bit negligent, and I apologize. Why does that negative sign need to be there? Say that one more time.
Equilibrium. I don't know if it's right.
Tell me, I don't.
They're equal because it can't go out.
Okay, and I think what you're saying, I think where you're going is the frog sitting on the desk, right? And the frog sitting on the desk is in equilibrium. Is that kind of where your head was? Yeah. So that. It is true that the forces acting on the frog have to put the frog in equilibrium. The difference here, though, is that these two forces are not acting on the same object. Are you with me there? It's weird, and it's kind of hard to get your head around. So the frog story, why aren't you working, is Earth on frog and table on frog. And both of those two things are on frog, right? These two forces have to be equal because it's in equilibrium. It's not accelerating. It's not moving, blah, 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 blah. These two forces do not have to be equal because it's in equilibrium. Remember I said that Newton's third law is Newton's third and most important law? This is more fundamental. This is more important than all of this frog business. This is saying that if I apply a force to a chair, the chair applies a force to me. And the force that I apply to the chair is exactly the same as the chair applying a force to me. Same magnitude, okay? Anytime a force exists, a second force exists, they act on opposite objects. Those two forces have to be the same in magnitude. And what does this negative sign tell us then? They're in opposite directions. That's the key to that negative sign. So I want you to write that down if you haven't done that already. Because, and you're like, we've been writing this down for the last 3 weeks, Ms. Carpling. I know, I get it. But I'm hoping that in the next 2 minutes, oh my gosh, 1 minute, I can prove to you that that's really where we're at and what we're doing. Okay, so I'm going to do this really fast. You can watch the video again and slow it down, and then you can listen to it at a normal pace. F equals ma, yeah? So this is the mass of A times the acceleration of A equals the mass of B times the acceleration of B. Oops, come on. Whoa, hi. Really? Oh, friends. Come on. I would like to write in orange. The mass of A times the change in velocity of A divided by time equals the mass of B times the change in velocity of B divided by time. Who pushes longer, A or B? Same time, right? I push on you the same amount of time as you push on me. Oops, and there are negative signs in here. See, I always drop these negative signs, and I should not. Do not drop the negative sign, okay? The principle here is that the momentum of A, the change in momentum, right? Mass times velocity for A should be equal to the change in momentum for B, except opposite. In your lab, what you should, fingers crossed, find is that these two values here are the same in magnitude and opposite in direction. If cart A gains momentum, cart B has to lose the same amount of momentum. That's Newton's third law. That's all it is. These should be the same magnitude okay? They should be opposite direction. Or opposite sign, opposite size. Okay? That's what you should, fingers crossed, find, or get something pretty darn close to. Okay? So in your homework for today, you had a couple of problems where you were going to calculate that, and you had a couple of problems where you were explaining what was happening. I'm trying to figure out here. We've got 6 minutes. I want to go through one problem with you right now. Let's do 205, number 1. Page 205, number 1. It says, a 44-kilogram student on inline skates. You guys okay? Do you need something? I just want to make sure you're here with me. Okay? 44-kilogram student on inline skates playing with a 22-kilogram exercise ball, ignoring friction, blah, blah, blah. So the student standing on skates is holding a big exercise ball. Okay? The student holds the ball and they're at rest. The student then throws the ball, causing the student to glide backward. Does that make sense? So if I take that ball and I throw it this way, the ball's going to go that way. I'm going to go this way. That is because of momentum, because of the conservation thereof, right? That's what we're talking about. So, mass of the person, mass of the ball, initial velocity of the person, initial velocity of the ball, final velocity of the person, final velocity of the ball. Conservation of momentum says that the mass of the person, or the mass of A, times the velocity of A at the beginning, plus the mass of B times the velocity of B at the beginning, has to be the same as the mass of A times the velocity. Oops. I'm not consistent in the way that I write this, and I apologize for that. At the end, plus the mass of B times the velocity of B at the end. Okay. The question for part A says, if the student glides back at 3.5 meters per second, we'll call that backwards, so we'll call it negative. How fast does the ball go? Can you figure that out? We know the initial velocity is 0. We know the masses 44 and 22. Can you figure that out? The initial velocity is 0, isn't it? So the total momentum at the beginning is 0. This is just like the one where Gonzo was jumping off of the boat. Is that okay? Does that make sense to you what I'm saying? Yeah? 44 kilograms times negative 3.5 meters per second plus 22 kilograms times the final velocity. Is that all right? Yeah. Part B says, explain what happens to the ball in part A in terms of momentum. Can you explain to me what happens in part A in terms of momentum? We've kind of written it out, but in words? What's the momentum of the ball at the beginning? 0. What's the momentum of the kid at the beginning? 0. What's the momentum of the kid at the end? Ryan, you think you want to say something? What are you going to say? Negative 3.5 times 44, because momentum is mass times velocity, right? So it's going to be this times this, that product. So what is that number? I don't know. Somebody do that. Somebody do it already. 44 times 3.5. 154. If the kid has a momentum of negative 154, tell me about the momentum of the ball. What does it have to be?
1.
Why?
Because they have to be equal.
Because they have to be equal, right? Because they have to add up to 0. One at the beginning, one at the end. Okay? For homework, I want you to actually, if you have not yet, I want you to go through this set of homework. I don't want you to move on to the new homework because I don't feel like that would be a good plan or fair. Okay? So, page 205, number 1, number 4, and 203, number 3. If you want to write those answers down, go ahead and do that. Make sure you have those done. I will look for them tomorrow. I want to see them completed tomorrow. Okay? Thanks, guys.